All right, guys, good morning. It's really nice for me to talk to you again, even though it's weird. I'm sitting in my own living room, talking to my computer, but I know that you're at the other side, so it makes it worth it. So, we are going to continue to look at arrays. We have completed our sorting algorithms, and you have now the choice whether you choose the selection sort or the bubble sort. Whatever you find easier, choose one because it doesn't make sense to know both or to remember both because both of them do exactly the same thing, sorting our array in an alphabetical or from smaller to largest or largest to smaller. So it sorts our array. So today we are going to move on and we're going to look at an algorithm to search a sorted array. Now we've already in chapter 7 looked at finding an element in an array, in an unsorted array, and we called that a linear search. And I'm going to compare both of these algorithms with you. So the linear search is for an unsorted array, and the binary one is for a sorted array. We can apply a linear search algorithm to a sorted array as well, but you will see in my example just now that it really does not make sense to use a linear search algorithm for a sorted array because a binary search is much more efficient. So let's look at the linear search then. In our example, it is a sorted array because I want to use the example for this, for both. But let's just pretend this is an unsorted array. Let's say we have to find the name Mary. Now we can see Mary is in position 6, but can you imagine this array having 15,000 elements and you have to find Mary? There's no way that you can know in which position Mary is found. So what do? We have to start in the beginning and search all the way through. Hence the word linear. So we start in position 1. We have our search value, which is Mary, and we ask the question, is Mary equal to whatever is in position 1 of our names? In this case, no, it is not. Is it bigger than, the second one, the third one, and so on? So we ask the same question again and again and again until we find Mary in our array. In our case, this was 6 times. And I want you to remember this number. 6 times we had to ask the question of whether we have found it or not. Now, with a binary search, our approach is slightly different. So again, we have our names with 7 elements. And again, we are looking for the name Mary. But our starting point will now not be the beginning, but rather the middle. Why? Because the middle, in that way, we can cut off asking half of the questions. Let's say, and in our case, if that's true, Mary is bigger than the middle. Then we're cutting out, asking it, this 3 times already. So we are cutting in round 1 already half of the times, elements we're cutting out of our search. So you can see that this would, in a big array, be very much more efficient. So how do we find the middle? We find the middle by taking our lower index plus the upper index, and we divide it by 2. And it's an integral division because our index that we find cannot be a floating point number or of a real data type, because our names position is of ordinal type. If you don't know what I mean by ordinal type, you must look that up again, because you should know what that means. So it has to be an integer, and we find the middle by adding these two up and dividing it by 2. And then we can ask this question, okay, is Mary in position 4 of our names? If not, we can ask, is it smaller than that? So we're asking, if it is smaller, and the answer is yes, what we have to do is we are going to change our upper bound, not from position 7 to the middle minus 1, because we know it's not the middle, so we have to check there. So I upper bound and I lower bound and I upper bound, which is now 3. If we add them in finding the middle again, 1 plus 3 equals 4, div 2 equals 2. So we find our new middle, which is 2. Again, cutting out half. So it goes finding the middle, checking if it's either smaller or bigger, and finding the middle. So, or if it's bigger, then the middle is equal to, or the lower bound now is equal to the middle plus 1. So if it's smaller, the upper bound becomes I middle minus 1. If it's bigger, I lower bound becomes I middle plus 1. And we do the same calculations again. The 5 plus 7 equals 12. Div 2 becomes 6. So our middle becomes Mary. And we ask ourselves the question. So in our case, yes, we have found Mary. So where the linear search took 6 questions, now it was only twice. Is it Kahlito bigger or smaller? It's bigger. Okay, new middle is Mary. Is it the same? Yes, done. So in an array with 15,000, so we cut out in the first round about 7,500 search results. So now our middle is 7,500. Now we're asking, is it bigger or smaller? Let's say it's smaller. Okay, 7,500 divided by 2, is 3,750, something like that. And then we cut another 3,500, elements out, search points out. And then we half that again. And you can imagine that by halving something, very quickly you shrink the number of elements that are left. So in our case, we're going to ask, we found, but let's say our name is actually Linda. So we're asking, is it smaller? Yes. So our middle was 6, but because it's smaller, our upper bound becomes now I middle minus 1. So it becomes 5. The lower bound is also 5. So now we're going to do simple calculation again. Okay, 5 plus 5 is 10, div 2 is 5. So the middle also becomes 5. And we're asking, is Mary or is Linda in position 5? Yes, it is. And our loop finally ends. But if it's bigger, we'll do exactly the same as we've done over here. So let's have a look at our algorithm, which is right here. So we're getting our search value, the name, let's say Mary. We initialize our position to 0 because we do not know where it is yet. And be found, our flag, we set to false, our lower index to 1, and our upper 1 to the number of elements in the array. And now we're looping through the array, while the lower bound and the upper bound are smaller or equal to each other. And be found is not true. We do this. So we find the position, the middle position. We're asking the question, is our search value. Can we find it in the middle? If yes, then our position becomes the middle and be found is true. And as soon as we hit the while loop again, it will stop now because be found is true now. If this is not the case, we haven't found our value, we're going to ask, okay, is it bigger? If it's bigger, then the lower bound becomes I middle plus 1. If not, hence it's smaller, then I upper bound becomes I middle minus 1. And we're ending in the while is end, and it repeats through the while until it finds our element. Or if it's not there, then we can display a message, sorry, name not found. Right, so what I want you to do now is I want you to skip through activity 5.1. I'm going to give you some of my grade 10 work that covers trace tables. It's very nice, and you need to know how to do trace tables for your theory exams. You've had them last year already and you suffered a little bit, but I'm not going to say that so loud. But it's actually easy marks that you can get. So focus on activity 5.2. The interfaces are already given for you in your data files, and there's a text file, and you have to search for a specific element. So I hope that you find this easy enough to be able to complete this activity. If you don't know, you can ask me anytime. Thank you, guys.